Good evening, and welcome to the Late Lab. I'm very glad you found your way here tonight. Before we settle into things, tell me where you're listening from. Maybe you're already tucked into bed. Perhaps you've got the lights turned low at the end of a long day, or maybe this is simply keeping you company while the rest of the world grows a little quieter. Wherever you happen to be, get comfortable, let your thoughts slow down, and make yourself at home for a while. And if these slow journeys through science are something you enjoy, you can always leave a like and subscribe. It helps this little corner of the internet continue to grow. If you've already done that, thank you for coming back and spending another evening here. It genuinely means a great deal. Tonight, though, we're going to spend some time in one of the strangest gaps in all of physics. Not what happens when a particle is measured, but what on earth it was doing just before that moment arrived. Because with an ordinary object, this seems almost too easy to ask. A stone is somewhere before you look at it. A train follows a particular track whether anyone is watching or not. But shrink things down to the quantum world, and that comfortable certainty begins to disappear. An electron can behave as though several possibilities remain open at once. Its quantum state can spread, evolve, interfere, and contain outcomes that have not yet become definite. And when a detector finally records something, one clear result appears. So what was there a moment earlier? Was the particle secretly in one definite place all along? Was it genuinely suspended between different possibilities? Or does the question itself assume that quantum reality works far more like the everyday world than it actually does? Hopefully we can investigate all of that without keeping you awake until sunrise. So, get comfortable, let the room become a little quieter, and let's begin. What actually happens to a particle before you measure it? Before we can ask what happens to a particle before it is measured, there is a deceptively simple question hiding underneath it. What exactly do we mean by before? With an ordinary object, the answer seems obvious. Imagine placing a marble inside a closed box. Even while the lid is shut, we naturally assume that the marble is somewhere in the box. It has a particular position. If it is rolling, it has a particular speed and direction. Opening the box does not seem to create those properties, it simply allows us to discover them. That comfortable assumption runs very deep. Classical physics was built around the idea that physical objects possess definite properties whether anyone happens to know their values or not. A planet has a location even when no telescope is pointed toward it. A falling stone has a velocity even if nobody bothers to calculate it. Ignorance belongs to us, not to the object. Quantum mechanics changes that picture in a rather profound way. An electron, photon, atom, or other quantum system is not generally represented as a tiny classical object carrying a complete collection of hidden labels telling us exactly where it is, how fast it is moving, which path it is following, and what result every possible future experiment will reveal. Instead, quantum mechanics represents the system using a quantum state. That quantum state contains the information needed to predict the probabilities of different possible measurement outcomes. Depending on the situation, it can describe possibilities for position, momentum, energy, spin, and other measurable physical quantities. But those possibilities do not always behave like ordinary ignorance about values that already exist. This is where the word measurement can cause unnecessary trouble, because it sounds suspiciously as though a human being needs to be involved. In physics, measurement does not simply mean somebody looking at something. A measurement is a physical interaction through which information about some property of a system becomes correlated with another physical system capable of recording it. An electron might strike a detector and produce an electrical signal. A photon might be absorbed by a light-sensitive material. An atom might pass through a magnetic field and emerge along one of several distinguishable paths. None of these processes requires a physicist to be standing nearby with an unusually intense expression. The apparatus can perform the interaction automatically. The result can be recorded while everyone in the laboratory is asleep. So when physicists talk about a particle before measurement, they usually mean something more precise than before somebody looks. The particle has first been prepared in some quantum state. Perhaps an electron has been emitted from a source. Perhaps a photon has passed through a polarizing device. Perhaps an atom has been cooled and trapped using carefully controlled electromagnetic fields. Once that preparation has taken place, the quantum state evolves. If the system is sufficiently isolated, that evolution follows the ordinary dynamical laws of quantum mechanics. The state does not simply sit there waiting patiently for a detector to take an interest in it. It changes with time according to the physical conditions surrounding it. And this is where classical intuition starts becoming unreliable. Suppose we prepare an electron and later measure its position. It is tempting to imagine that the electron must have possessed one exact position all along, even if we did not know what that position was. Sometimes that kind of reasoning is harmless, but quantum mechanics does not generally require such a picture, and in many situations it actively resists it. There is an important difference between not knowing a value and a quantum state failing to assign that quantity a single definite value in the first place. Consider a shuffled deck of cards lying face down. The top card already has a definite identity. Perhaps it is the Queen of Hearts. You simply do not know that yet. Turning the card over reveals information that already existed. Quantum uncertainty can be different. A quantum system may be prepared in a state for which a particular measurement has several possible outcomes, with the theory assigning probabilities to each of them. Treating this merely as ignorance about a secretly predetermined answer does not reproduce all of the behavior observed in quantum experiments. Interference experiments are one reason physicists know this distinction matters. Bell tests provide another. The mathematical structure of quantum mechanics itself makes it difficult to assign simultaneous definite values to every possible observable in the way classical intuition would prefer. An observable is simply a measurable physical quantity, such as position, momentum, energy, or a component of spin. The uncomfortable part is that asking what value every observable possessed before measurement may not always correspond to a question that quantum mechanics answers. That does not mean nothing exists before measurement. It does not mean reality switches off when nobody is watching. And it certainly does not mean human consciousness magically summons particles into existence. What exists in the standard mathematical description is a quantum state, and that state evolves in a precise and experimentally successful way. The mystery lies in deciding what that state represents physically. Some interpretations of quantum mechanics treat the quantum state as a fundamental part of reality. Others describe an underlying physical configuration beneath it. Some treat measurement outcomes as relative to interacting systems. Others modify the dynamics so that definite outcomes physically emerge. These interpretations can disagree sharply about the story being told, while agreeing remarkably well about what experiments will actually show. That distinction matters. There are things quantum mechanics predicts with extraordinary precision, and there are deeper questions about what its mathematics means that remain genuinely debated. So the puzzle is not simply that we have failed to look closely enough. It is that nature appears to use a description in which possibilities, amplitudes, and measurable outcomes are woven together in a way that does not fit comfortably inside the classical picture of a tiny object quietly carrying all of its properties around with it. Before the detector produces its answer, something very real is evolving. The difficult question is what exactly that something is. Before a particle can be measured, physicists usually need to do something that sounds almost mundane compared with the mysteries of quantum mechanics. They need to prepare it. A quantum experiment does not normally begin with a completely unknown particle wandering into a laboratory by chance. The system is produced, filtered, cooled, accelerated, trapped, or otherwise manipulated so that at least some features of its quantum state are known. This process is called state preparation. For an electron, preparation might involve an electron gun that emits electrons with a controlled range of energies. A photon might be produced by a laser and then passed through a polarizing filter. An atom can be cooled with carefully tuned laser light and confined using electromagnetic fields. Neutrons can be selected according to their energies or spin states. In high-energy physics, entire particle accelerators are devoted to producing very specific kinds of particles under controlled conditions. The exact machinery changes dramatically from one experiment to another, but the purpose is similar. Physicists want to know what kind of quantum state they are starting with. That detail matters because the phrase unmeasured particle can otherwise create a slightly misleading picture. It can sound as though the particle has never interacted with anything before the moment a detector finally notices it. In reality, preparation itself involves interactions. A photon passing through a polarizing filter has interacted with matter. An electron accelerated by an electric field has interacted with that field. An atom held inside a trap is continuously influenced by the electromagnetic forces keeping it confined. So when we say that a particle has not yet been measured, what we usually mean is that it has not undergone the particular measurement whose outcome we are interested in. Imagine preparing photons so that they all have the same polarization. Those photons may already have passed through several pieces of apparatus. But if the experiment is designed to measure their polarization along a different direction later, that later measurement is still genuinely undecided according to the quantum state. This distinction between preparation and measurement is one of the quieter but more important ideas in quantum experiments. Nothing simply appears from nowhere in a mysterious fog of uncertainty. The experiment begins with known conditions, and once those conditions have been established, quantum mechanics tells us how the state should evolve and what probabilities should be expected when a later measurement is finally performed. There is another important reason for preparing particles carefully. Quantum mechanics is fundamentally statistical when it comes to measurement outcomes. Suppose an experiment predicts that a particular measurement has two possible results, each occurring with equal probability. Measuring one particle only gives one result. Perhaps the detector records the first possibility. That alone tells us very little. So the experiment is repeated. Another particle is prepared in as nearly the same quantum state as possible. Then another. Then another. Modern experiments may repeat such procedures thousands, millions, or even billions of times. If the preparation is reliable, the distribution of measured outcomes can then be compared with the probabilities predicted by quantum mechanics. This repetition is one of the reasons the theory can be tested so precisely. Quantum mechanics may not tell us exactly what one particular particle will do in an individual probabilistic measurement, but it can predict the statistical pattern produced by a large collection of identically prepared systems with remarkable accuracy. There is a subtle phrase hidden inside that description. Identically prepared does not always mean absolutely identical in every microscopic detail. Real laboratories are not perfectly isolated from the universe. Temperatures fluctuate slightly. Electromagnetic fields contain noise. Equipment vibrates. Particles may become entangled with degrees of freedom that experimenters do not monitor. This leads to an important distinction between pure quantum states and mixed states. A pure state represents the most complete quantum state information that ordinary quantum mechanics allows us to assign to the system. If a photon has been prepared in a precisely specified polarization state, for example, it may be treated as being in a pure state for the purposes of the experiment. But sometimes the preparation leaves genuine statistical uncertainty about which state has been produced. Perhaps half of the systems were prepared one way and half another without the experimenter knowing which is which. That can be described using a mixed state. A mixed state can also arise when a system becomes entangled with its environment. Even if the larger combined system is described by a pure state, the smaller subsystem considered on its own may behave as though it is mixed because some information has effectively become distributed into the surrounding environment. To handle both situations, quantum mechanics uses a mathematical object called the density matrix. The density matrix is a more general description than an ordinary wave function. It can represent pure states, ordinary statistical mixtures, and the reduced states of systems entangled with things outside the part of the experiment being examined. That might sound like an intimidating piece of mathematics, but the physical idea is gentle enough. The experimenter needs a description of what has actually been prepared, including any uncertainty that preparation itself introduces. Only then does it make sense to ask what happens afterward. And this changes the original mystery slightly. The question is not really what a completely undefined particle does in some mysterious interval before somebody decides to look at it. The particle has a history. It has been produced somehow. It has interacted with equipment. Its quantum state has been shaped by a preparation procedure. Then, for some interval, that state evolves before the measurement of interest takes place. That interval is where the strange part begins. Because once the preparation is complete, quantum mechanics gives us an extraordinarily precise description of how the state changes. What it does not always give us is the comfortable classical story we instinctively want to place underneath that description. Once a quantum system has been prepared, physicists need some way of describing what has actually been prepared, and this is where one of the most famous objects in quantum mechanics appears: the wave function. During the 1920s, two very different mathematical approaches to quantum theory emerged. Werner Heisenberg developed matrix mechanics, a formulation built around measurable quantities and the mathematical relationships between them. Soon afterward, Erwin Schrödinger developed wave mechanics, which described quantum systems using wave functions that evolve through time. At first, these approaches looked almost like competing theories. They were written in very different mathematical languages and seemed to offer quite different pictures of what was happening. But physicists soon discovered that they were mathematically equivalent. They produced the same observable predictions. The wave function became especially useful because it offers something that feels almost visual. For a single particle, we can describe a wave function associated with position. Instead of assigning the particle one exact point in space, that wave function can extend across a region. And this is where the temptation to imagine a tiny physical wave begins. It is worth resisting that temptation. The wave function is not simply a little ripple of material spread through space in the same way that a wave spreads across the surface of a pond. What it assigns are probability amplitudes. These amplitudes are mathematical quantities associated with different possible configurations of the system. When the particle is later measured, Those amplitudes are used to calculate the probabilities of the different outcomes that might be recorded. For position, that means the quantum state may contain amplitudes associated with many different locations. If the wave function is concentrated tightly around one small region, a position measurement is very likely to find the particle there. If the wave function is spread broadly across space, the possible detection locations are correspondingly spread out. This has encouraged one of the most common phrases in popular descriptions of quantum mechanics. The particle is everywhere at once. It sounds wonderfully mysterious. It is also very easy to misunderstand. A spread-out wave function does not necessarily mean that an ordinary little object has somehow been chopped into countless miniature copies, with one tiny electron sitting at every possible location. Quantum mechanics is saying something more subtle. The state contains coherent amplitudes associated with different possible positions, and those amplitudes can combine and interfere in ways that ordinary classical probabilities cannot. That distinction becomes important, because an electron is not merely a fuzzy ball of matter smeared through space. When it is detected, the interaction is localized. A detector records an event in one place. Yet before that event, the quantum state may have been extended across a much larger region. The same state can also be represented in completely different ways. Instead of describing possible positions, physicists can represent the state in terms of momentum, or energy, or spin. These different descriptions are called different bases. A position basis asks how the quantum state is distributed among possible positions. A momentum basis describes amplitudes associated with different momenta. A spin basis can describe amplitudes for different possible spin measurement outcomes along a chosen direction. None of these descriptions is simply a photograph of what the particle secretly looks like. They are different mathematical representations of the same quantum state. And this is an important clue. In classical physics, we are accustomed to imagining that there should always be one complete underlying picture. A ball has a position and a velocity. If we knew enough detail, we could imagine taking a perfect snapshot of everything at a particular instant. Quantum mechanics does not fit naturally into that kind of picture. The state contains information that behaves differently depending on which physical quantity we choose to examine. There is another unusual feature hidden inside the wave function. Probability amplitudes have something called phase. Phase is essential because amplitudes do not simply behave like ordinary probabilities, they can combine. Two amplitudes can reinforce one another, increasing the probability of a particular result. They can also oppose one another, reducing that probability, sometimes all the way to zero. This is the foundation of quantum interference. One subtle distinction matters here. If the phase of an entire isolated quantum state is shifted by the same amount, nothing observable changes. This is called a global phase. But differences in phase between parts of a superposition can have dramatic physical consequences. These relative phases determine how different alternatives interfere. So two quantum states that might look almost identical if we considered only the sizes of their amplitudes can produce very different experimental patterns because their relative phases differ. This is one reason the wave function cannot be interpreted as an ordinary cloud of probabilities. A classical probability distribution simply tells us how uncertain we are about different possibilities. A quantum state carries additional information through probability amplitudes and their relative phases. And that information can later reveal itself through interference. This brings us back to the strange interval before measurement. If the particle has not yet been detected, quantum mechanics does not simply hand us a hidden photograph showing where the particle really was all along. Instead, it gives us a quantum state. That state may be spread across space. It may contain several possible outcomes. It may have carefully defined relationships of phase between those possibilities, and it may look very different depending on which basis we use to represent it. The mathematics is extraordinarily precise. What remains less obvious is what kind of physical reality that mathematics is describing. The wave function may be the most complete description quantum mechanics gives us, but whether it should be imagined as something physically real, something informational, or something pointing toward a deeper level of reality is a question on which physicists have never completely agreed. So before measurement, we do have a description, just not the tiny hidden picture our classical instincts keep asking for. Once a quantum state has been prepared, it does not simply wait in place until somebody decides to measure it. It evolves. That point is easy to overlook because so much attention in quantum mechanics falls on the strange moment when a measurement produces a definite result. But between preparation and measurement, the theory gives a remarkably clear account of what happens to the quantum state. For an isolated, non-relativistic quantum system, that evolution is described by the Schrödinger equation introduced by Erwin Schrödinger in the 1920s. The equation is one of the central laws of quantum mechanics. Its role is, in some ways, similar to the role played by Newton's laws in classical physics. If the initial quantum state is known, and if the physical influences acting on the system are known, then the Schrödinger equation determines how that state changes with time. This is an important detail because quantum mechanics is often described as though everything inside it is random. That is not quite true. Before a measurement, the evolution of the wave function is deterministic. If we know the initial state accurately enough, and know the physical conditions surrounding it, then the theory specifies the later state. There is no need to imagine the wave function making spontaneous choices every few moments. The randomness appears when particular measurement outcomes are considered. The ordinary evolution in between is remarkably orderly. At the centre of the Schrödinger equation is a mathematical object called the Hamiltonian. The Hamiltonian represents the energy of the system and the interactions that influence its behaviour. For a simple particle moving freely through empty space, the Hamiltonian contains the kinetic energy associated with its motion. If the particle experiences an electric field, a magnetic field, or another potential, those influences are incorporated as well. The Hamiltonian therefore acts rather like a description of the physical landscape through which the quantum state evolves. Change that landscape, and the future state changes with it. Consider a particle whose position is initially reasonably well localized. Its wave function may form what physicists call a wave packet, meaning that most of the probability amplitude is concentrated within a limited region of space rather than spread evenly across the universe. If the particle then travels freely, that wave packet generally spreads. This is not because the particle is bumping into invisible obstacles or because the experiment is gradually losing track of it. The spreading follows directly from quantum evolution. A localized wave packet contains a range of different momentum components. Those momentum components evolve with different phases as time passes. As their relative phases change, the shape of the wave packet changes as well. The result is that a state that began narrowly concentrated can become broader. If a position measurement is made much later, the range of locations where the particle might be detected can therefore be wider than it was earlier. For very massive objects, this spreading can be extraordinarily small on ordinary human timescales, which is one reason we do not usually notice tables and cups developing dramatically uncertain positions during breakfast. For microscopic particles, however, wave packet spreading can be an important and measurable part of their behaviour. External influences can reshape the quantum state too. An electron moving through an electric potential will evolve differently from one moving freely. A magnetic field can alter states associated with spin or orbital motion. Even gravity can influence quantum evolution. Experiments with neutrons, atoms, and other quantum systems have observed phase shifts caused by gravitational potentials. None of this requires a measurement to occur. That distinction matters. An interaction is not automatically a measurement. A particle can encounter a force or pass through a controlled field while remaining part of a coherent quantum evolution. What matters for measurement is whether the interaction creates information about a particular observable in another physical system in a way that can become distinguishable or recorded. A magnetic field that gently changes the phase of a quantum state is not necessarily measuring it. A detector that becomes correlated with one of several possible outcomes is doing something fundamentally different. Throughout ordinary isolated evolution, quantum mechanics describes the state as changing unitarily. Unitary evolution is the mathematical rule that preserves the total probability contained in the quantum state. If all possible outcomes together had total probability equal to certainty before the evolution, they still do afterward. Probability amplitude may move from one possibility to another. Relative phases may change. Wave packets may spread, split, overlap, and interfere. But the overall quantum state evolves in a controlled and reversible mathematical manner. This gives the period before measurement a surprisingly calm structure. The quantum state is not repeatedly collapsing for no reason. It is not flickering randomly between different hidden classical realities. According to the standard dynamics, it follows a precise evolution determined by its initial state and Hamiltonian. And then measurement seems to introduce something very different. Suppose a quantum state has evolved into a superposition associated with several possible measurement results. Before the measurement, the Schrödinger equation allows those components to remain together as part of one evolving state. When the experiment is performed, however, only one definite result is actually recorded in an ordinary laboratory run. The detector clicks here rather than there. A spin measurement produces one outcome rather than the other. A photon appears at one detector rather than another. The theory gives probabilities for these possibilities, but it does not normally tell us in advance which individual result will occur. This creates one of the deepest tensions in quantum mechanics. The evolution of the wave function before measurement is deterministic. The outcome obtained when the measurement is performed is probabilistic. One part of the theory describes a smooth, continuous evolution. The other appears to produce one definite result selected from several possibilities. And that contrast is not a minor technical inconvenience. It is the mathematical heart of the measurement problem. Before the detector acts, quantum mechanics gives us a state evolving with remarkable precision. The mystery is why that beautifully continuous evolution seems to end, at least from our point of view, with one unmistakably definite answer. Superposition is one of those ideas that sounds almost deliberately designed to make quantum mechanics feel strange. But at its core, the principle is simple. A quantum state can contain several possible outcomes at once, not as an ordinary list of things that might secretly be true, but as a coherent combination of alternatives that can later influence one another. That difference is crucial. Imagine a classical coin hidden beneath your hand. It is either heads or tails. You may not know which, but the answer already exists. Your uncertainty is simply a lack of information. A quantum system can behave differently. Suppose we prepare the spin of an electron in a particular way. Spin is a quantum property that does not have a perfect classical equivalent. Although it behaves in some respects like an intrinsic form of angular momentum, If the electron is prepared to have a definite spin outcome along one chosen axis, then a measurement along that same axis can produce a predictable result. But if we instead measure the spin along a different axis, the original state may be represented as a superposition of the possible outcomes for that new measurement. This does not mean the electron is literally spinning in several ordinary directions at once, like a microscopic toy top having an identity crisis. It means that the quantum state contains amplitudes associated with more than one possible result. Those amplitudes matter because they are not just probabilities. They also contain phase information. And phase is what allows quantum alternatives to interfere. Consider a particle travelling through an interferometer. An interferometer is a device designed to split a quantum state into different possible paths and then bring those paths back together. A photon, for example, can encounter a beam splitter that creates a coherent superposition of two path alternatives. One part of the quantum state is associated with one route, another part is associated with the other. If the paths later recombine, their corresponding probability amplitudes can add together. Depending on their relative phase, they may reinforce one another, that is constructive interference. Or they may partially or completely cancel, that is destructive interference. The final probability of detecting the particle at a particular output, therefore, depends on the relationship between the alternatives while the particle was still unmeasured. This is why superposition is not merely a fancy way of saying that physicists do not know what happened. If the particle had simply chosen one path or the other in the ordinary classical sense, and the experimenter merely lacked that information, the interference pattern would generally not be reproduced. The alternatives have to remain coherent. Quantum coherence means that the relative phases between components of the state are preserved well enough for interference to occur. That word, coherence, draws a useful boundary between a genuine quantum superposition and an ordinary mixture. Imagine again that a particle could travel along path 1 or path 2. In a classical mixture, half of the particles might really take path 1 and half might really take path 2. You simply do not know which path any individual particle followed. If the two groups are combined later, you add ordinary probabilities. There is no phase relationship between the alternatives capable of producing quantum interference. A coherent superposition behaves differently. The two path amplitudes remain part of a single quantum state. When they overlap again, the amplitudes combine before probabilities are calculated. That small mathematical distinction produces very real experimental consequences. It can create bright regions where detections are common and dark regions where detections are strongly suppressed. The particle is not merely carrying two independent possibilities in a mental list. The alternatives are physically relevant within the structure of the quantum state. This is one reason phrases such as being in two places at once need to be handled carefully. They can be useful as a first approximation, especially when discussing a spatial superposition, but they easily create the wrong image. A particle in a superposition of two locations is not necessarily best imagined as a tiny classical object duplicated into two complete copies. Quantum mechanics is describing one state with components associated with different possible locations. Those components can later interfere, and it is that ability to interfere that tells us the superposition was not equivalent to ordinary ignorance. The same principle applies beyond position. A quantum system can be in a superposition of energy states. It can be in a superposition of spin outcomes. Photons can occupy superpositions of polarization states. Atoms and molecules can occupy spatial superpositions. Carefully engineered superconducting circuits can even be placed into coherent superpositions involving different collective electrical states. The exact physical meaning depends on the system, but the mathematical principle remains the same. Several alternatives are represented together within one quantum state. This changes the meaning of what it means for a particle to have a property before measurement. In classical physics, we tend to assume that every measurable property already has one definite value. Quantum mechanics does not generally work that way. A state can be definite with respect to one observable while being a superposition relative to another. An electron can have a definite spin outcome along one axis, while lacking a single definite outcome for a spin measurement along a different axis. That does not mean the theory is incomplete, simply because it refuses to supply a complete classical list. The behavior predicted from those superpositions has been tested repeatedly. Interference experiments work precisely because the relative amplitudes and phases remain physically significant before detection. This persistence of coherence is one of the clearest clues we have about the strange interval before measurement. The particle cannot generally be treated as though it already possesses every classical answer, and the detector merely reveals whichever label was hidden inside. Something richer is happening. The quantum state carries multiple alternatives together. Those alternatives evolve. Their phases change. They can separate and recombine. And as long as coherence survives, they can influence the probabilities of events that have not yet occurred. So superposition does not mean that reality is simply doing everything imaginable at once. It means that before measurement, the quantum description can contain several mutually exclusive possibilities within one coherent state. And until something destroys the coherence or a measurement produces a definite record, those possibilities are not merely irrelevant uncertainties. They remain part of the physics. Quantum mechanics contains a rather peculiar mixture of certainty and uncertainty. The quantum state itself can evolve in a perfectly predictable way, while the result of a later measurement may still be impossible to predict with certainty. That tension became much clearer through the work of Max Born. In the 1920s, Born proposed the interpretation that connected the wave function to measurable probabilities. The wave function itself contains probability amplitudes. These amplitudes are not ordinary probabilities, and they can be positive, negative, or even complex quantities. To turn them into the probabilities of actual measurement outcomes, quantum mechanics uses what became known as the Born rule. In simple terms, the probability associated with a particular result is obtained from the squared magnitude of the corresponding probability amplitude. That may sound like a small mathematical detail, but it changes the role of the wave function completely. The wave function does not directly say that a particle is 50% here and 50% there in the same way that a classical probability table might. Instead, it assigns amplitudes to possible outcomes. Those amplitudes can interfere with one another first. Only after that interference has been taken into account do the final probabilities emerge. This is why phase matters so much. Two alternatives with similar amplitudes can produce a high probability in one situation and almost no probability in another, depending on their relative phase. So the quantum state contains more structure than an ordinary list of chances. Yet when an actual measurement is performed, the outcome appears as one definite result. Suppose an electron is prepared so that a spin measurement along a chosen direction has two possible outcomes with equal probability. Quantum mechanics predicts that if the measurement is repeated many times, roughly half of the results should fall into one category and roughly half into the other. But for the first electron, the theory does not ordinarily tell us which one will occur. The second electron may produce the opposite result. The third may match the first. The sequence can look irregular and unpredictable. and that is not because the laboratory has suddenly become careless. Even when experimenters reproduce the preparation and measurement procedure as precisely as possible, individual outcomes can still differ. This has been demonstrated repeatedly across many kinds of quantum systems. Photons can be prepared in the same polarization state and then measured along another direction. Atoms can be prepared in nearly identical internal states. Electrons can be sent through the same apparatus. Each individual event may be uncertain, but the overall pattern is not arbitrary. As more measurements accumulate, the relative frequencies tend toward the probabilities predicted by quantum mechanics. If the theory predicts one outcome with a probability of about 1/4 and another with a probability of about 3/4, a small set of trials may wander away from those proportions. A larger set usually comes closer. With sufficiently many repetitions, the statistical pattern becomes extremely stable. This is one of the quiet strengths of quantum mechanics. The theory can be extraordinarily precise about what a large collection of experiments will produce, even while remaining silent about which particular result will occur in one individual run. That combination feels strange because classical physics trained us to expect something else. If we knew the exact position and velocity of a classical ball and understood every force acting on it, then in principle its later trajectory could be calculated. Any uncertainty would normally come from incomplete knowledge. Quantum mechanics does not generally work that way. The quantum state can be known as completely as the theory allows, yet a future measurement may still have several possible outcomes. The uncertainty is built into the predictions of the state itself. At least, that is how the standard formalism presents it. This does not mean that every interpretation of quantum mechanics agrees that nature contains fundamental randomness. That distinction is important. In the de Broglie-Bohm interpretation, for example, particles possess definite configurations, and their motion is guided by the wave function according to deterministic equations. The uncertainty appears because the exact underlying configuration is generally not known. In Everettian approaches, often associated with the many worlds interpretation, the universal quantum state evolves continuously without a fundamental random collapse. Different outcomes become associated with different branches of the total state. In objective collapse models, genuine random collapses are introduced as physical processes. Other interpretations place more emphasis on the probabilities representing information, expectations, or relations between systems. So when we ask what probability means before measurement, we have reached a point where the mathematics remains clearer than the interpretation. What the theory tells us operationally is straightforward. A prepared quantum state determines probabilities for the possible results of a chosen measurement. Those probabilities can be tested by repeating the experiment many times. The observed frequencies agree with the predicted distributions with impressive accuracy. What the theory does not settle by itself is what those probabilities represent physically before the outcome is recorded. Are they genuine possibilities in nature? Do they reflect uncertainty about a deeper configuration? Do all outcomes persist in different branches? Or are the probabilities describing the information available to an observer about future experiences? Different interpretations answer those questions differently. But there is one point on which the experimental evidence is much less ambiguous. The probabilities are not optional decorations added to the theory. They are central to its predictive structure. Before measurement, the quantum state evolves according to precise mathematical rules. When a particular observable is measured, that state supplies a probability distribution over the outcomes that may be recorded. The individual result can remain unpredictable even when the preparation has been controlled with extraordinary care. And so the strange interval before measurement contains both order and uncertainty at the same time. The state evolves predictably. The probabilities evolve predictably. The eventual individual outcome may not. Quantum mechanics therefore gives us something more unusual than simple ignorance. It gives us a world in which the laws can specify the possibilities with extraordinary precision while leaving the next single result genuinely open, at least according to the standard description. Of all the experiments used to make quantum mechanics feel unsettling, few are as simple in appearance as the double-slit experiment. The basic arrangement seems almost innocent. Take a barrier with two narrow openings. Send something toward it. Place a screen behind the barrier and record where whatever passed through eventually arrives. If you did this with tiny classical pellets, the result would be easy to imagine. Some pellets would pass through one opening, some through the other, and the screen would gradually develop two broad clusters behind the two slits. Waves behave differently. In the early 19th century, Thomas Young demonstrated that light passing through two openings could produce an interference pattern. Instead of two simple bright regions, alternating brighter and darker bands appeared. The explanation was familiar from other kinds of waves. A wave passing through one slit spreads out. Another wave spreads from the second slit. Where their crests reinforce one another, the resulting wave becomes stronger. Where a crest from one meets a trough from the other, they can partially or completely cancel. For light, this was powerful evidence of wave behavior. Then quantum mechanics made the story considerably stranger. Particles such as electrons can produce interference too. Claus Jensen carried out influential electron diffraction experiments in the 20th century that demonstrated this wave-like behavior. Later experiments, including celebrated work associated with Akira Tonomura and his colleagues, made the effect especially vivid by recording individual electrons one at a time. At first, the screen looks almost random. One electron arrives at one location, another lands somewhere else. Each detection is localized, as though a tiny particle has struck one particular point. Nothing resembling a wave appears in any individual impact, but continue sending electrons through the apparatus, one after another, and something remarkable begins to emerge. Thousands of isolated dots gradually form an interference pattern. The electrons arrive like particles. Their statistical distribution behaves as though wave-like alternatives have interfered. And crucially, the electrons do not need to be travelling through the apparatus in a crowd for this to happen. The experiment can be arranged so that the particles pass through one at a time, separated enough that ordinary interactions between different electrons cannot explain the pattern. Each particle contributes one dot. Yet after many repetitions, those dots build the pattern predicted by quantum interference. This brings us directly back to what happens before measurement. Suppose both possible paths are available and no usable information is produced that tells us which one the particle followed. Quantum mechanics assigns a probability amplitude to the alternative associated with one path and another amplitude to the alternative associated with the other. Those amplitudes remain coherent. When they later contribute to the same possible detection locations, they interfere. At some places, the amplitudes reinforce each other, at others they cancel. The eventual probabilities therefore depend on both alternatives. This makes it difficult to tell a simple classical story in which the electron definitely went through one slit while the other slit became completely irrelevant. If that were all that happened, then blocking or opening the unused slit should not alter the statistical distribution produced by electrons that supposedly travelled through the other one. But it does. Changing which alternatives are physically available changes the interference pattern. The quantum state therefore evolves in a way that depends on the complete experimental arrangement. This does not force us to imagine the electron as a tiny solid sphere literally cutting itself into two halves. Nor does it mean that one complete classical electron necessarily squeezes through each opening. Those pictures are attempts to force the quantum state into familiar imagery. What the theory actually says is more careful. The state contains coherent amplitudes associated with both possible paths. As long as nothing makes those alternatives distinguishable, their relative phase remains capable of influencing what happens later. Then comes the detection. However spread out the quantum state may have been, the detector does not usually record a faint fraction of an electron across the entire screen. It records one localized event. One electron appears at one place, the next electron appears somewhere else. Only after many such detections does the interference pattern reveal itself, so the strange behavior is not simply found at the moment the particle hits the detector. It is encoded in the evolution that occurred before the detection. Something about the unmeasured quantum state preserved both path alternatives well enough for them to influence the probabilities of where the final event could occur. And there is an important qualification here. The phrase "nobody checks" can sound as though human attention is responsible. It is not. What matters is whether physical information about the path becomes available through an interaction. If a detector, atom, photon, or other part of the environment becomes correlated with the alternatives strongly enough to distinguish them, the interference can be reduced or disappear. Nobody needs to read the result. Nobody even needs to know that the information exists. The physics depends on the interaction, not on a conscious observer staring at a screen. This is what makes the double-slit experiment so valuable. It turns the abstract idea of superposition into something experimentally visible. Before detection, the particle cannot generally be treated as an ordinary classical pellet with one known or unknown root, while every other possibility is irrelevant. The available alternatives remain part of the quantum state. They evolve together, they retain phase relationships, and they influence the pattern of events that eventually appears. Then, after all of that smooth and strangely distributed quantum behavior, the detector gives one tiny definite click. The mystery is not whether something happened before that click. The interference pattern tells us that something certainly did. The mystery is what kind of reality could behave like that, while no definite path had been recorded. The double-slit experiment becomes even more revealing when we make one small change. We try to find out which path the particle took. At first that sounds harmless. If the particle passed through one opening or another, why not simply place a detector near the slits and check? Classically, this should only give us more information. But in quantum mechanics, gaining path information changes what can happen afterward. This idea is closely connected to Niels Bohr's principle of complementarity. Bohr argued that certain experimental arrangements reveal different, mutually exclusive aspects of a quantum system. One arrangement may be designed to reveal interference. Another may be designed to reveal which path the particle followed. But the clearer the path information becomes, the less visible the interference generally becomes. The two descriptions are not simply incomplete views of one ordinary hidden trajectory. They correspond to different physical experimental conditions. Suppose a particle approaches two possible paths. If nothing in the environment records which route is associated with the particle, the two alternatives can remain coherent. The corresponding probability amplitudes retain a definite relationship of phase. Later, when the alternatives are brought back together, those amplitudes can interfere. But now imagine placing a path detector beside the apparatus. The detector does not need to stop the particle. It does not even need to absorb it. It only needs to interact differently depending on which path is taken. If the particle follows one route, the detector may enter one physical state. If it follows the other, the detector may enter another. The particle and detector then become entangled. This means the quantum state of the particle can no longer be described independently in the same way. One path alternative is correlated with one detector state. The other path alternative is correlated with another. If those detector states are distinguishable enough, the interference visible in measurements of the particle alone becomes reduced. The reason is not that somebody has looked at the detector. The reason is that information about the path has become physically encoded somewhere else. That distinction is extremely important. A human observer is not required. The detector could record the information and immediately erase its display. The data could be stored on a computer that nobody ever checks. The interaction might involve a photon scattering from the particle and flying away into the laboratory. As long as the surrounding world becomes correlated with the alternatives in a way that can distinguish them, the coherence available to the particle by itself can be lost. So when quantum mechanics says that observation affects the system, the word observation can be misleading. It is not eyesight. It is not consciousness. It is interaction and information becoming physically available. Imagine trying to determine which slit an atom passes through by shining light near the openings. A photon scatters from the atom. In principle, the direction of the scattered photon can reveal which path the atom took. But that photon is now carrying information about the atom. The atom and photon have become correlated. If the path information is sufficiently reliable, the interference pattern weakens. The scattered photon does not need to reach a human eye. It can drift into the laboratory wall and disappear. The important event already happened when the correlation was created. This relationship between path information and interference has been explored in many forms. Experiments with photons have shown that interference visibility decreases as distinguishability between paths increases. Similar principles have been demonstrated with atoms and molecules. Interference experiments have even been carried out with large molecules containing hundreds or thousands of atoms, showing that quantum coherence is not limited to individual elementary particles. The larger the system becomes, however, the harder it is to keep the alternatives isolated from the environment. A large molecule can interact with thermal radiation. It can collide with stray gas molecules. It can emit photons. Each of these interactions can carry away information about where the molecule is, and every piece of escaped information can make the different alternatives more distinguishable. This is one reason quantum behavior is so delicate at larger scales. The environment is constantly trying, in a purely physical sense, to learn what is happening. There is also a smooth trade-off between path information and interference. It is not always an all-or-nothing choice. If the two detector states are only partly distinguishable, some coherence may remain. The interference pattern becomes less pronounced, rather than disappearing completely. If the path information becomes nearly perfect, the interference visibility can approach zero. This reveals something important about what measurement really is. A measurement is not necessarily a dramatic moment when a mysterious boundary is crossed. It can be understood as a gradual process in which a quantum system becomes correlated with other physical systems. As those correlations grow stronger, information about certain alternatives spreads outward. The original superposition becomes harder to observe as interference within the smaller system. This also helps explain why the phrase measuring disturbs the particle is only partly satisfactory. Yes, measurements involve interactions, and those interactions can alter a system. But the deeper issue is not simply that a detector gives the particle a mechanical shove. The important change is that the alternatives become distinguishable. the detector acquires information. The environment becomes correlated with the system. Quantum coherence is redistributed into the larger combined state. In principle, if every part of that interaction remained perfectly controlled, the coherence of the larger system could still exist. In practice, once information spreads into many uncontrolled degrees of freedom, recovering that coherence becomes extraordinarily difficult. This is where the boundary between an untouched quantum alternative and a recorded outcome begins to look much less mysterious. The particle is not waiting for a person to notice it. It is interacting with a physical world capable of storing information. And when that world becomes capable of telling one alternative from another, the interference that revealed the coherent superposition begins to fade. So learning the path changes the quantum state not because knowledge itself has magical power, but because information has to be carried by something physical. A detector must interact. A photon must scatter. An environment must become correlated. Once that happens, the different possibilities are no longer quietly overlapping in the same way. They have begun to leave different traces in the universe. Quantum uncertainty is often described as though it simply means our measurements are not good enough. That explanation is tempting, but it misses the central point. Werner Heisenberg's uncertainty principle is not merely a statement about clumsy instruments, imperfect laboratories, or particles being disturbed because we tried to look at them too closely. It is a statement about the structure of quantum states themselves. The most famous example concerns position and momentum. Position tells us where a particle is. Momentum describes its motion, combining its mass with its velocity in the non-relativistic case. Classically, there is no fundamental reason why a particle cannot possess an exact position and an exact momentum at the same instant. If our instruments are poor, we may fail to determine those values accurately, but the values themselves are still assumed to exist. Quantum mechanics changes that assumption. In 1927, Werner Heisenberg introduced the uncertainty principle. Soon afterward, Earl Hesse Kennard gave a precise mathematical relation for position and momentum, and Howard Percy Robertson later developed a more general form that applies to a wide range of quantum observables. The key idea is that certain pairs of observables are mathematically incompatible. Physicists describe them as non-commuting observables. Position and momentum are the classic example. The more narrowly a quantum state is concentrated in position, the more broadly its possible momentum values must be distributed. And the reverse is true as well. A state with a very sharply defined momentum must be spread more widely across position. This relationship is built into the mathematics of quantum mechanics. It is not simply caused by measurement. One way to understand this is to think again about a wave packet. A particle that is strongly localized in space is described by a wave packet concentrated within a small region. But creating that narrow wave packet requires combining many different momentum components. Those components overlap in just the right way to produce a sharp concentration in position. If instead the state contains only a very narrow range of momenta, the corresponding wave is much more extended in space. So localization in one description naturally produces spreading in the other. The two are connected. Heisenberg originally discussed uncertainty partly through imagined measurement processes, including the famous thought experiment involving a microscope attempting to locate an electron using light. The act of scattering a photon from the electron can disturb the electron's momentum. That is a real physical effect. But it is not the whole uncertainty principle. Even if we imagine perfect instruments that introduce no unnecessary experimental error, the quantum state itself can still possess intrinsic spreads in position and momentum. That distinction matters enormously. Measurement disturbance concerns what happens when an apparatus interacts with a system. Quantum uncertainty concerns what ranges of outcomes are already encoded in the state before that measurement occurs. Suppose a particle is prepared in a state with an extremely narrow position distribution. If we repeat that preparation many times and measure position, the results will cluster closely together. But if we prepare the same state repeatedly and measure momentum instead, those results will show a much broader distribution. The particle has not become uncertain because the momentum detector was poorly designed. The broad range of possible momentum outcomes was already part of the structure of that prepared quantum state. This connects directly to the question of what exists before measurement. A classical picture would suggest that the particle possesses one precise position and one precise momentum at all times. Perhaps we simply do not know either value. But standard quantum mechanics does not generally describe the system that way. For incompatible observables, a state cannot assign arbitrarily sharp values to both simultaneously. This does not mean that every property is always vague. A quantum system can be prepared in a state with a very definite value of one observable, but doing so usually affects the range of possible outcomes for another incompatible observable. The uncertainty is therefore structured. It follows precise mathematical rules, and those rules have been confirmed experimentally again and again. This is another reason the hidden classical picture becomes difficult to maintain. The particle before measurement is not simply described as a tiny object with a complete set of exact coordinates that happen to be concealed from us. The quantum state itself has a different architecture. Some quantities can be sharp, others must remain distributed. Which ones can be simultaneously definite depends on the mathematical relationships between the observables involved. So uncertainty in quantum mechanics is deeper than imperfect knowledge. It is not merely a fog covering an otherwise perfectly classical reality. It is part of the framework used to describe what the system is capable of revealing. And before any detector produces a result, that structure is already there. A measurement in quantum mechanics is not simply the moment when somebody looks at a screen. It is a physical interaction. That sounds almost obvious, but it removes one of the most persistent misunderstandings surrounding quantum theory. A measuring device is made of matter. It contains atoms, electrons, electromagnetic fields, circuits, sensors, and sometimes large numbers of carefully engineered components. So if quantum mechanics applies universally, then the measuring apparatus should itself obey quantum mechanics. This creates an immediate puzzle. In the early 20th century, John von Neumann developed an influential mathematical description of measurement in which the quantum system and the measuring apparatus are treated together. Suppose a particle is in a superposition of two possible outcomes. Perhaps an electron is in a state that could produce one spin result or another. Before measurement, those possibilities are represented together within the quantum state. Now imagine the electron interacting with a detector. If the first possible outcome occurs, the detector is pushed into one corresponding physical state. If the second possible outcome occurs, the detector is pushed into another. Quantum mechanics then describes the combined system as becoming entangled. One component of the state contains the electron with the first result correlated with the detector showing the first reading. Another component contains the electron with the second result correlated with the detector showing the second reading. The detector has not merely uncovered a hidden label, it has become physically correlated with the quantum alternatives. This is where measurement begins to look much more like an ordinary physical process. A microscopic event occurs. That event influences a detector. The detector amplifies the effect. And eventually the result becomes large enough to leave a stable record. Consider a photon entering a light detector. The photon may be absorbed by matter and transfer its energy to an electron. That electron can trigger further electrical activity. The tiny microscopic event is amplified until an electrical pulse becomes large enough to be registered by laboratory equipment. In another detector, an incoming particle might cause a flash of light. Elsewhere, it might leave a mark on photographic material. Modern experiments can convert microscopic interactions into illuminated pixels, voltage changes, digital values, or stored computer records. The final result looks thoroughly classical. One detector clicked, one pixel lit up, one number was stored. There is no faint half-click corresponding to every possible outcome, and this is where the difficulty appears. The detector is also a quantum object, so why does the combined quantum description seem capable of containing several correlated alternatives, while our experience contains only one definite record? John von Neumann's formalism makes this problem especially clear. We can begin by treating only the particle quantum mechanically and imagine the detector as an external measuring device. But there is no obvious reason to stop there. The detector is made of atoms, so we can include it in the quantum description. Then we can include the electronics connected to the detector. Then the computer storing the result. Then more of the laboratory. In principle, the boundary between the measured system and the rest of the world can be moved farther and farther outward. This sequence is sometimes called the von Neumann chain. The particle becomes correlated with the detector. The detector becomes correlated with the electronics. The electronics become correlated with a stored record. The laboratory environment becomes correlated with all of them. Each stage spreads information about the original quantum event into a larger physical system. Eventually, the difference between the possible outcomes becomes macroscopic. A vast number of particles may now occupy different states depending on what happened at the microscopic level. At no point does a human mind need to intervene for this process to occur. That point deserves to be made carefully. Quantum measurement is sometimes described in popular culture as though reality patiently waits for consciousness. Nobody looks, so the particle remains uncertain. Someone opens the door, and the universe finally makes up its mind. That is not how ordinary laboratory quantum mechanics works. A detector can operate in an empty room, an experiment can run automatically overnight, a computer can store the outcome for days before anyone examines it. The relevant physical interactions occur whether a person is present or not. There is no established physical law stating that consciousness is required to trigger an ordinary quantum measurement. The confusing language comes partly from the historical use of words such as observer and observation. In physics, an observer can simply mean a physical system that interacts with another system in a way that makes information available. A detector qualifies perfectly well. So the real mystery of measurement is not whether anything happens physically. Plenty happens. Particles interact. Quantum states become correlated. Microscopic differences are amplified. Information spreads into larger systems. Stable records appear. The difficult part is understanding how this process relates to the appearance of one definite result. If the underlying quantum evolution treats the system and apparatus together, then the mathematics can naturally produce entanglement between different possible outcomes and different detector states. Yet when an experimenter eventually checks the equipment, only one record is encountered. The question is therefore not why looking causes something magical to happen. It is why an interaction governed by quantum mechanics seems to give rise to a world in which measurements have definite outcomes. That is a much sharper problem. it keeps the mystery inside physics rather than placing it inside human awareness, and it changes the way we think about the moment of measurement. A measurement is not a mysterious glance. It is a chain of physical correlations. A tiny quantum event becomes connected to something larger. That larger system becomes connected to something larger still. Eventually, the result is written into the macroscopic world strongly enough that it can be treated as a stable fact. The unresolved question is why, out of all the possibilities present in the quantum description, that fact appears to us as one particular outcome. The word collapse is responsible for a remarkable amount of confusion in quantum mechanics. Before a measurement, the quantum state can evolve smoothly according to the Schrödinger equation. A superposition can persist. Different probability amplitudes can remain coherent. Their phases can change continuously with time. Then a measurement is made. One definite result appears. The traditional way of describing this change is to say that the wave function collapses. Suppose an electron is prepared in a superposition of two possible spin outcomes. Before measurement, both possibilities are represented within the quantum state. When the spin is measured, the apparatus records only one result. If that particular outcome is obtained, the quantum state is then updated so that it corresponds to the result that was actually observed. This is the collapse postulate. It is extremely useful. It tells physicists how to update the state after a measurement so that later predictions agree with the result already recorded. But it also introduces a deep conceptual problem. Ordinary quantum evolution and collapse do not look like the same kind of process. Between measurements, the Schrödinger equation describes continuous deterministic evolution. Given the initial state and the Hamiltonian, the later state follows according to a precise mathematical rule. Collapse appears very different. Several possible outcomes are represented before measurement. Then one particular result is obtained. The state changes abruptly to one compatible with that result, and the individual result is generally probabilistic. This difference is the heart of what became known as the quantum measurement problem. The problem is not that physicists do not know how to calculate laboratory predictions. They do. The standard rules of quantum mechanics work extraordinarily well. The problem is deciding what those rules are telling us about reality. Is collapse an actual physical event? Does something in nature literally jump from a superposition into one definite state? Or is collapse only a change in the description we use after new information becomes available? That question has never received a universally accepted answer. Niels Bohr and Werner Heisenberg became strongly associated with approaches later grouped together under the Copenhagen interpretation. That label can be slightly misleading, because Bohr and Heisenberg did not hold identical philosophical views. There was never one perfectly unified Copenhagen doctrine. Still, the broad family of views emphasized that quantum mechanics gives predictions for the outcomes of experiments, and that classical concepts remain essential when describing measuring arrangements and recorded results. For practical laboratory work, this approach is remarkably effective. Treat the microscopic system quantum mechanically. Describe the measuring apparatus in ordinary classical terms. Use the Born rule to calculate possible outcomes. When one result is obtained, update the quantum state accordingly. The calculations work. The awkward question is where this division between quantum system and measuring apparatus actually comes from. A detector is made of atoms. Those atoms contain electrons and nuclei. The electronics attached to the detector are also physical systems. If electrons obey quantum mechanics when they are inside the experiment, why would they suddenly stop obeying it when they become part of the measuring equipment? There is no obvious fundamental line in nature labelled quantum objects on one side and classical apparatus on the other. In practice, physicists can choose a useful boundary and calculate perfectly well. Fundamentally, however, the location of that boundary is much harder to explain. Erwin Schrödinger highlighted this difficulty in 1935 with his famous cat thought experiment. Imagine a cat placed inside a sealed box with a device linked to a quantum event. Perhaps the decay of a radioactive atom triggers a mechanism that determines whether the cat survives. If the microscopic quantum event remains in a superposition, and if every part of the apparatus follows ordinary quantum evolution, then the mathematics appears to connect the different microscopic possibilities with different macroscopic outcomes. One component corresponds to the atom not decaying and the cat remaining alive. Another corresponds to the atom decaying and the cat dying. Schrödinger was not seriously proposing that everyday cats routinely occupy bizarre half-alive and half-dead conditions. The thought experiment was intended to expose the difficulty of extending quantum superposition without limit from microscopic systems into the macroscopic world. At what point does one definite outcome appear? The atom? The detector? The mechanism? The cat? The person opening the box? Once that question is asked, the measurement problem becomes difficult to avoid. Eugene Wigner pushed the idea further with another thought experiment. Imagine an observer inside a laboratory performing a quantum measurement. From the observer's own perspective, a definite result is obtained. But someone outside the sealed laboratory could, in principle, attempt to describe the observer, apparatus, and measured system together as one larger quantum system. Now the puzzle reaches the observer as well. Does collapse occur when the detector records something? When the person inside becomes aware of it? When the outside observer learns the result? Or does no fundamental collapse occur at all? Modern physics provides no experimental requirement that human consciousness has a special role in ordinary measurement. That is important. Wigner's thought experiment is valuable because it exposes the logical depth of the measurement problem, not because it proves that minds magically control reality. The operational rules remain excellent. Physicists prepare quantum systems, calculate probabilities, perform measurements, update states, and obtain astonishing agreement between theory and experiment. But beneath those successful calculations sits an unresolved question. Continuous quantum evolution seems capable of preserving multiple alternatives. Ordinary experience presents one result. Collapse is the traditional bridge between them. Whether that bridge represents a genuine physical process, an effective description, or something that should disappear from a deeper interpretation of quantum mechanics, remains one of the most persistent questions in the foundations of physics. One of the most natural ways to escape the strangeness of quantum mechanics is to imagine that the particle really does have definite properties before we measure it. Perhaps the quantum state is simply incomplete. Maybe an electron already knows what result it will produce, even if we do not. This possibility was taken very seriously by Albert Einstein. In 1935, Einstein, Boris Podolsky, and Nathan Rosen published an argument questioning whether quantum mechanics provided a complete description of physical reality. Their reasoning involved entangled quantum systems. Entanglement occurs when two quantum systems are described by a shared state whose properties cannot generally be reduced to two independent states, one belonging to each particle. Once entangled particles are separated, measurements performed on them can display correlations stronger than anything that seems natural from an ordinary classical picture. Einstein was deeply uncomfortable with the idea that events occurring far apart might be connected in a way that appeared incompatible with local causality. One appealing possibility was that the particles carried additional information from the beginning. Imagine producing two particles together and sending them in opposite directions. Perhaps each particle leaves the source carrying a hidden set of instructions. If one is later measured in a particular way, its hidden instructions determine the answer. The distant particle carries corresponding instructions of its own. The observed correlations could then seem mysterious while actually being predetermined from the moment the particles separated. In that kind of picture, quantum mechanics would be incomplete rather than fundamentally indeterminate. The missing information became known more generally as hidden variables. For decades, the disagreement remained largely philosophical. Then John Stuart Bell found a way to turn it into an experiment. In 1964, Bell showed that a broad class of theories based on local hidden variables must obey mathematical limits, now known as Bell inequalities. The basic idea can be understood without following the full mathematics. Suppose two distant particles carry predetermined instructions that determine how they will respond to several possible measurements. If those instructions were established locally before the particles separated, and if nothing can influence the distant measurement faster than light, there is a limit to how strongly the measurement results can be correlated. Quantum mechanics predicts that entangled particles can exceed that limit. Suddenly, the disagreement was testable. Nature could be asked. In 1972, Stuart Friedman and John Clauser performed an important early Bell test using entangled photons. Their results supported the quantum predictions rather than the local hidden variable alternatives being tested. During the early 1980s, Alain Aspect and his collaborators carried out increasingly sophisticated experiments in France, including tests in which measurement settings were changed rapidly while photons were travelling toward their detectors. Later experiments associated with Anton Zeilinger and many other researchers extended Bell tests across larger distances, improved detectors, and developed increasingly careful methods for choosing measurement settings. Again and again, Bell inequalities were violated. The strongest modern tests have gone further by addressing weaknesses known as experimental loopholes. Earlier Bell tests often had to make additional assumptions because detectors missed some particles or because the measurement stations were not sufficiently separated to exclude certain slower-than-light explanations. In 2015, independent experiments closed the major detection and locality loopholes simultaneously. One prominent experiment, led by Bas Henson, used entangled electron spins in diamond separated by roughly 1.3 kilometers in the Netherlands. Other groups performed loophole-resistant tests using entangled photons. These results strengthened the experimental rejection of the locally causal hidden variable explanations targeted by Bell's theorem. It is important, however, not to turn Bell's theorem into a claim stronger than it really is. Bell did not prove that nothing exists before measurement. He did not prove that particles possess no physical properties. And he certainly did not prove that human consciousness creates reality. What Bell's theorem tells us is more precise. The observed quantum correlations cannot be reproduced by theories that retain the relevant combination of locally causal influences and predetermined hidden variables assumed in Bell's argument. Something in that classical picture has to give. That distinction matters because hidden variable theories have not disappeared completely. David Bohm's interpretation of quantum mechanics, for example, gives particles definite positions. But Bohmian mechanics is explicitly non-local. The guiding dynamics connecting entangled systems do not preserve the simple local picture Einstein hoped might sit beneath quantum mechanics. So Bell's theorem does not force us into one interpretation. Instead, it dramatically narrows the possibilities. The universe cannot simply be explained by saying that every particle carries a little local answer sheet containing the result of every measurement it might encounter. The experimental correlations are too strong. There is another strange feature worth keeping clear. Although entangled particles produce correlations that violate Bell inequalities, those correlations cannot be used to send a controllable message faster than light. Each observer sees an individual sequence of outcomes that appears random. One experimenter cannot choose a particular result and force the distant particle to produce a corresponding message. The remarkable correlations become visible only when the results from both sides are later compared. Relativity therefore survives intact as far as faster-than-light communication is concerned. And this leaves us with a much deeper answer to the original question. Before measurement, we cannot safely imagine that a quantum particle is simply carrying every possible answer in advance in the straightforward local classical sense. Nature has been tested on precisely that possibility. It does something more subtle. Whatever reality exists beneath the quantum state, it must be capable of producing correlations that cannot be explained by ordinary local hidden instructions. Bell transformed one of the deepest philosophical disagreements in physics into something that could be tested in a laboratory, and nature answered by making the familiar classical explanation much harder to keep. Bell's theorem makes it difficult to imagine that distant quantum particles simply carry local hidden instructions telling them how to respond to every possible measurement. But there is another obstacle to the classical picture, and this one does not even require separating particles across large distances. It is called quantum contextuality. The idea is subtle, but the question behind it is familiar. Could a quantum system possess a complete collection of definite properties before measurement, with the apparatus simply revealing whichever property we choose to inspect? At first, that seems like a reasonable possibility. Perhaps position already has a value. Perhaps spin along every possible direction already has a value. Perhaps energy, angular momentum, and every other observable all carry definite answers in advance. We may not know those answers, but perhaps the particle does. In the 1960s, Simon Kochen and Ernst Specker showed that quantum mechanics places severe limits on this idea. Their result became known as the Kochen-Specker theorem. The theorem concerns something called non-contextuality. Non-contextuality is the assumption that if a physical quantity possesses a definite value, that value should not depend on which other compatible quantities happen to be measured alongside it. That sounds almost unavoidable from a classical point of view. Imagine measuring the length of a table. You would not normally expect the table's length to change merely because you also decided to measure its width. The value belongs to the table. The surrounding measurement context seems irrelevant. Quantum mechanics does not generally permit such a simple assignment. Kochen and Specker showed that for quantum systems with the appropriate mathematical structure. It is impossible to assign predetermined values to all relevant observables in a way that both reproduces the predictions of quantum mechanics and keeps those values independent of measurement context. In other words, you cannot always imagine the system carrying a complete answer sheet in which every possible question already has one fixed response. The relationships between those answers become inconsistent with quantum theory. This result is different from Bell's theorem. Bell's theorem focuses strongly on locality. It asks whether correlations between separated systems can be explained by locally predetermined properties. The Kochen-Specker theorem does not depend on spatially separated particles in the same way. Its central issue is contextuality. The question is whether the result associated with a particular observable can be regarded as a fixed, pre-existing value that is independent of the other compatible measurements performed in the same experimental arrangement. Quantum mechanics says that such a universal non-contextual assignment cannot reproduce all of its predictions. This makes the mystery of the unmeasured particle even deeper. Suppose we wanted to preserve a thoroughly classical picture. We might imagine that the quantum state is incomplete, and that underneath it lies a hidden catalogue of actual properties. Every possible observable would have a definite value. Measurement would merely uncover the appropriate entry. But the Cauchy-Specker theorem tells us that this catalogue cannot be constructed in the straightforward context-independent way we might expect. The result associated with a measurement cannot generally be understood as though it were simply sitting inside the particle with complete independence from the physical measurement context. That does not mean the experimenter's thoughts create the answer. Context in this setting means the physical arrangement of compatible measurements, not the opinions or awareness of a person in the laboratory. The apparatus matters because different experimental arrangements correspond to different sets of observables being jointly examined. The mathematics of quantum mechanics ties those possibilities together in ways that a classical collection of independent hidden values cannot satisfy. This is not merely an abstract mathematical curiosity. Researchers have developed experimental tests of contextuality using several different kinds of quantum systems. Photons have been used in arrangements involving polarization and different possible measurement settings. Trapped ions have provided highly controlled systems in which carefully chosen observables can be tested. Neutron interferometry has also been used to examine contextual quantum correlations. Across these different platforms, experiments have found results consistent with the contextual predictions of quantum mechanics and incompatible with the relevant non-contextual models being tested. There are practical complications, as there are in almost every foundational experiment. Real devices are imperfect. Measurements contain noise. Experimental tests often rely on inequalities or carefully constructed assumptions that allow the ideal theorem to be confronted with real data. But the broad conclusion has survived increasingly precise examination. The classical idea that every observable simply possesses a fixed context-independent value before measurement is not sufficient. And this helps clarify what physicists mean when they say that quantum properties can depend on the measurement context. They are not saying that reality is unreal. They are not saying that particles have no properties at all. And they are not saying that the universe waits for human attention. The claim is more precise. Quantum measurement outcomes cannot generally be explained by imagining that every possible measurable quantity carried a predetermined value that would have been revealed identically regardless of which other compatible measurements were performed. That restriction is profound. Interference already showed that quantum alternatives can remain coherent before detection. Bell's theorem showed that locally predetermined instructions cannot reproduce the full strength of entangled correlations. Contextuality now tells us that even without relying on distance separation, a simple collection of measurement-independent hidden values cannot account for the whole quantum structure. Taken together, these results make the ordinary classical story increasingly difficult to maintain. The unmeasured particle may certainly possess a physical reality. Quantum mechanics does not require us to say otherwise. But whatever that reality is, it cannot generally be described as a tiny object carrying a complete set of ordinary. Context-independent answers waiting patiently for us to read them. The choice of what is measured is tied to the structure of what can meaningfully be assigned, and that is one of the most important lessons hidden beneath the mathematics. Before measurement, the particle is not merely an unopened box filled with classical facts. The quantum state contains relationships between possible measurements that are more tightly woven together than that picture allows. When a result finally appears, it belongs not just to an isolated hidden property, but to a physical measurement context governed by the rules of quantum mechanics. Some quantum experiments seem, at first glance, to suggest something even stranger than uncertainty or superposition. They can make it look as though a decision made in the present changes what a particle did in the past. That sounds dramatic. Fortunately, it is also not what the experiments require us to believe. The idea was sharpened by John Archibald Wheeler through what became known as the delayed choice experiment. Wheeler wanted to challenge the assumption that a quantum particle must always possess one definite classical history before we decide how to measure it. Imagine a photon entering an interferometer. The device gives the photon two possible routes. If those routes are later recombined in the right way, the probability amplitudes associated with them can interfere. The final detection probabilities then depend on the relative phase between the two alternatives, but the apparatus can also be arranged differently. Instead of recombining the paths, it can preserve information that allows the experimenter to distinguish which route is associated with the photon. In one arrangement, interference is available. In the other, path information is available. So far, this resembles the usual lesson of complementarity. Wheeler's twist was to delay the decision about the final arrangement. The photon can already have entered the interferometer before the experiment determines whether the paths will be recombined or kept distinguishable. From a classical point of view, this sounds awkward. If the photon already travelled through the apparatus, surely it must already have decided what kind of behaviour it was displaying. If the final setup reveals interference, perhaps we are tempted to say that the photon must have behaved like a wave and explored both alternatives. If the final setup reveals path information, perhaps we are tempted to say that it must instead have behaved like a particle and chosen one route. But if the choice of measurement arrangement is made only after the photon has entered the experiment, then those classical stories start to look as though the future choice determines the earlier behaviour. That is the source of the apparent paradox. Quantum mechanics does not require that conclusion. The safer description is that the photon evolves according to its quantum state through the experimental arrangement. The theory assigns amplitudes to the physically available alternatives. What can later be inferred depends on the complete measurement context. If the paths are recombined coherently, interference can appear. If the arrangement instead preserves distinguishable path information, the results are described differently. Nothing needs to travel backwards through time. No future decision needs to reach into the past and physically alter something that has already happened. The problem arises mainly when we insist that the photon must have possessed one definite classical story throughout the experiment. Experiments inspired by Wheeler's delayed choice proposal have been performed using photons and other quantum systems. Their results agree with the ordinary predictions of quantum mechanics. The timing of the final measurement choice does not force the theory into retrocausality. Instead, the experiments show that assigning a measurement-independent classical history to the quantum system can be misleading. A related family of experiments is often described using the even more mysterious phrase delayed choice, quantum eraser. These experiments involve entangled systems and the presence or absence of which path information. In a typical arrangement, one particle is detected directly, while another correlated system carries information that can, depending on how it is measured, preserve or erase the possibility of distinguishing the path alternatives. When the data are later sorted according to the outcomes of the correlated measurements, interference patterns can appear within particular subsets. Other subsets display complementary patterns. But this does not mean that an interference pattern suddenly appears on an earlier screen after somebody makes a later decision. The unsorted detection events do not change. The earlier record remains exactly what it was. What changes is how correlations within the full data set are revealed when the results from different parts of the experiment are compared. This is an important distinction. A delayed choice quantum eraser cannot be used to send information into the past. An experimenter looking only at the earlier detections cannot determine what later measurement choice will be made. The interference structure becomes visible only after the relevant correlated results are brought together and sorted appropriately. So there is no message arriving before it was sent. No earlier event is physically rewritten. And no observer reaches backward through time merely by deciding which measurement to perform. The experiment is strange for a different reason. It shows how strongly our ordinary storytelling instincts depend on imagining that a particle must possess a single classical history independent of how the experiment is completed. Quantum mechanics often refuses to provide such a history. It gives us something else. It provides a quantum state evolving through a particular physical arrangement. It tells us which alternatives remain coherent. It predicts which correlations will appear. And it tells us what probabilities to expect once a particular measurement context is specified. What it does not always allow is the comfortable statement that the particle definitely travelled one ordinary route, possessed one complete set of classical properties, and merely waited for us to discover them later. The delayed choice experiment, therefore, does not show that the future changes the past. It shows that we should be cautious about forcing a classical past onto a quantum system when the experiment itself never established one. That lesson fits closely with everything already revealed by interference, uncertainty, Bell correlations, and contextuality. The quantum state can evolve perfectly consistently without providing a single measurement-independent classical narrative for every moment. We can predict the observations, we can calculate the correlations, we can repeat the experiment and verify the statistics, but if we insist on asking exactly what classical path the particle secretly followed before the measurement arrangement made that path meaningful, quantum mechanics may simply decline to supply one. The past has not been rewritten. It was our classical story about that past that was never guaranteed in the first place. If ordinary measurements seem too disruptive, there is an obvious question to ask. Could we simply measure more gently? Perhaps, instead of forcing a quantum system into one sharply defined outcome, we could interact with it so weakly that we gain only the faintest trace of information while disturbing the system as little as possible. That idea leads to weak measurement. In the late 1980s, Yakia Aharonov, David Albert, and Lev Vaidman developed the modern theory of weak values, showing that quantum systems could be probed through interactions far gentler than the strong projective measurements normally associated with definite outcomes. A conventional strong measurement tries to distinguish the possible results clearly. If an observable has several possible outcomes, the apparatus becomes strongly correlated with one of them, producing a definite reading. A weak measurement works differently. The interaction between the system and the measuring device is deliberately made very small, so small in fact that the result from one individual particle is usually almost useless. The signal produced by the quantum system may be buried beneath the natural uncertainty of the measuring apparatus. One weak measurement might barely shift a detector pointer at all. But that is the point. Because the interaction is weak, the system is disturbed less strongly. The price is that far less information is obtained from each individual trial. To recover anything useful, physicists repeat the experiment many times with systems prepared in the same way. The tiny shifts are then averaged. What was invisible in one measurement can become statistically clear across thousands or millions of repetitions. This already tells us something important about what weak measurement does not provide. It is not a magical method for watching one electron continuously while leaving it perfectly untouched. It does not allow an experimenter to secretly observe every detail of a particle's hidden journey without consequences. The information comes gradually, statistically, and through real physical interaction. An especially unusual feature appears when weak measurements are combined with post-selection. Post-selection means that after the weak interaction, a later stronger measurement is performed, and only trials producing a chosen final result are grouped together. The average weak measurement associated with that selected group can produce what is called a weak value, and weak values can behave in ways that look thoroughly strange. Suppose an observable ordinarily has measurement outcomes lying within a particular range. A weak value can sometimes fall outside that range. A quantity whose ordinary possible results might lie between two familiar values could produce a weak value apparently larger than either of them. At first sight, this sounds as though the particle briefly possessed an impossible property. That is not the right interpretation. A weak value is not generally equivalent to an ordinary measurement result possessed by one particle at one instant. It depends on the prepared state, the weak interaction, and the later post-selection. Its unusual magnitude arises from the quantum relationships between those ingredients. Treating it as a simple hidden classical value can therefore lead to very misleading conclusions. This becomes especially relevant when weak measurements are used to investigate paths. Experiments with photons have used weak measurement techniques to reconstruct average flow, like patterns associated with quantum evolution. Such results are sometimes described informally as showing the trajectories of photons. But care is needed. They do not demonstrate that each individual photon secretly followed one unique classical track through the apparatus. Instead, they reveal statistical information extracted from many similarly prepared quantum systems under weak interaction. The reconstructed structure belongs to the quantum measurement procedure and the ensemble of experimental results. Weak and continuous measurements have also been used with superconducting quantum devices, trapped atoms, and other carefully controlled systems. In continuous quantum measurement, a system is monitored repeatedly or continuously through a stream of weak interactions. Instead of one dramatic measurement occurring at a single instant, information gradually accumulates over time. The resulting record may look noisy. A detector produces a fluctuating signal, and that signal can be used to update the estimated quantum state continuously. From this process, physicists can construct what are called quantum trajectories. These trajectories show how the state of the monitored system changes when conditioned on the particular sequence of measurement results that was observed. They can be extraordinarily useful. Researchers can follow transitions in superconducting quantum circuits. They can watch quantum states wander under the combined effects of coherent evolution, environmental noise, and continuous measurement. They can even use the measurement record to apply feedback and control the system. But once again, the word trajectory needs some care. A quantum trajectory obtained from continuous measurement is not necessarily the revelation of an untouched path that existed before the monitoring began. The measurement itself is part of the dynamics. The system evolves while interacting with the detector. The stream of information obtained from the detector influences the state assigned to the system. A monitored quantum system is therefore physically different from an identical system left completely isolated. There is no free view through the window. To learn something, some interaction has to occur. This is the deeper lesson of weak measurement. Quantum mechanics allows physicists to make the interaction gentler. It allows them to trade information for disturbance. It allows subtle features of quantum evolution to be reconstructed from large collections of carefully controlled experiments. but it does not quietly restore the classical picture that earlier experiments made so difficult to sustain. There is still no general evidence that every unmeasured particle follows one perfectly definite, measurement-independent classical path that weak measurement merely uncovers. Instead, weak measurements reveal more of the structure already encoded in the quantum state and in its interactions with the measuring apparatus. They offer glimpses, very delicate ones. But those glimpses remain quantum. The closer we try to watch what happens between preparation and detection, the more clearly we discover that watching is itself another physical event. Even the gentlest measurement leaves a trace of its presence. Perfect isolation is one of those things that exists much more comfortably in equations than in ordinary rooms. A real quantum system is almost never completely alone. Even when physicists work extremely hard to isolate a particle, atom, molecule, or engineered quantum device, the surrounding world is still there. Photons pass through the environment. Gas molecules move through the apparatus. Thermal radiation is emitted and absorbed. Electric and magnetic fields fluctuate. Nearby matter vibrates. And every one of those interactions has the potential to carry away information about the quantum system. This is where decoherence becomes essential. The modern theory of environmental decoherence grew in important part from the work of Hans-Dieter Zeh, who argued that interactions with the environment could explain why quantum superpositions become effectively classical in appearance. Wojciech Zurek later developed these ideas in detail, particularly their connection to measurement, classical behavior, and the emergence of what are known as pointer states. The basic idea begins with entanglement. Suppose a particle is in a coherent superposition of two different positions. If it remained perfectly isolated, the relative phase between those alternatives could, in principle, remain available for interference. But now imagine that a photon from the surrounding environment scatters from the particle. If the particle is in one position, the photon leaves in one state. If the particle is in the other position, the photon leaves in a slightly different state. The particle and photon become entangled. Information about the particle's position has begun to leak outward. Now another photon scatters. Then a molecule from the surrounding gas interacts. Then more thermal radiation becomes correlated with the system. Very quickly, the two alternatives are no longer represented only by different states of the particle. Each alternative has become correlated with a different state of the surrounding environment. The information has spread. This process is decoherence. It does not necessarily destroy the total quantum state. If we could somehow describe the particle together with every photon, molecule, field, and other environmental degree of freedom involved, the larger combined system could still be represented by quantum mechanics. But if we look only at the original particle, something important has changed. The phase relationship between the alternatives has become effectively inaccessible. The information needed to observe interference is now distributed through the environment. Recovering it would require controlling all of those environmental correlations with extraordinary precision. For a small and carefully protected quantum system, physicists can sometimes preserve coherence for surprisingly long periods. That is one of the central technical challenges in quantum computing and quantum information experiments. But for ordinary macroscopic objects, decoherence can be fantastically rapid. Imagine trying to place a dust grain into a coherent superposition of noticeably different locations. A dust grain contains an enormous number of atoms. It interacts constantly with surrounding air molecules. It absorbs and emits thermal radiation. Countless photons strike it. each interaction can carry away some information about where the grain is. Under ordinary environmental conditions, coherence between macroscopically distinct positions can disappear on timescales far shorter than anything a human being could directly perceive. In some estimates for sufficiently large objects and well-separated alternatives, the relevant decoherence times can become almost absurdly tiny. The exact value depends strongly on the size of the system, temperature, separation between alternatives, surrounding gas pressure, radiation field, and other conditions. The important point is not one universal number. It is the enormous difference between an isolated microscopic system and an everyday macroscopic object constantly interacting with its surroundings. This helps explain why we do not normally see tables interfering with themselves. It is not because quantum mechanics simply switches off when objects become large. It is because large objects are extraordinarily difficult to isolate. Their quantum information becomes entangled with the environment almost immediately. When physicists describe only the smaller system and ignore all of those environmental degrees of freedom, they use what is called a reduced state. That reduced state can begin to look very much like an ordinary classical mixture. Suppose a quantum system originally contained two coherent alternatives. After strong environmental decoherence, the reduced description may look as though the system is simply in one alternative or the other with certain probabilities. The interference terms become extremely small. Locally, the coherent relationship between the alternatives is effectively gone. This resemblance to a classical probability distribution is one of decoherence theory's most important achievements. It explains how the familiar classical world can emerge in appearance from underlying quantum dynamics. Wojciech Zurich's work also emphasized pointer states. These are states that remain relatively stable under particular kinds of environmental interaction. The environment effectively selects certain states as robust, because information about them can be copied repeatedly into the surroundings without immediately destroying their identity. For many macroscopic systems, relatively well-localized positions behave in this stable way. That helps explain why everyday objects appear to occupy definite locations rather than obvious superpositions of widely separated positions. The environment continually records information about them. Light bouncing from a chair carries information about where the chair is. Air molecules colliding with it carry more. Thermal radiation carries still more. In that sense, the environment is constantly performing something remarkably similar to measurement. Not because it is conscious, not because it has an opinion about the chair, but because physical interactions continually establish correlations and spread information. This gives decoherence enormous explanatory power. It explains why interference is fragile. It explains why macroscopic superpositions are so difficult to observe. It explains why measuring devices develop stable records. And it provides a physical bridge between the quantum behavior of isolated systems and the classical appearance of the everyday world. But decoherence does not settle every question. Suppose the total quantum state still contains different decohered alternatives. One component corresponds to one measurement result and its surrounding environmental record. Another corresponds to a different result and a different environmental record. Decoherence explains why those alternatives stop interfering with one another for practical purposes. What it does not, by itself, universally explain is why one particular outcome is experienced as the unique result. Different interpretations of quantum mechanics answer that question differently. So decoherence removes much of the mystery surrounding how quantum possibilities become effectively separated, but it does not automatically solve the entire measurement problem. What it does show very clearly is that an unmeasured particle is rarely floating through a silent universe untouched. the surroundings are almost always interacting with it. Information is continually leaking outward. Correlations are continually forming. And once enough of that information escapes into the environment, the delicate coherence that made several alternatives behave as one quantum state becomes almost impossible to observe locally. The classical world does not necessarily appear because quantum mechanics stops. It may appear because quantum mechanics is happening everywhere at once. At this point, the strange part of quantum mechanics is no longer difficult to see. The theory works. Its predictions are extraordinarily accurate. Interference experiments behave as expected. Bell inequalities are violated in the way quantum mechanics predicts. Contextuality appears in the right places. Decoherence explains why large systems lose visible coherence so quickly. And yet the central question remains: what is actually happening? Different interpretations of quantum mechanics answer that question in very different ways. One broad family of views is usually grouped under the Copenhagen interpretation. There is no single perfectly unified Copenhagen doctrine, but the approaches associated with Niels Bohr and Werner Heisenberg generally resist the demand that every unmeasured quantum system must possess a complete classical description. The quantum state is used to predict the possible outcomes of measurements. The experimental arrangement matters. Certain questions have definite answers only within a particular measurement context. From this perspective, asking what exact classical path a particle followed before measurement may simply demand a kind of description that quantum mechanics does not provide. The theory tells us what can be predicted. It does not necessarily owe us a hidden classical story underneath those predictions. That is one way to live with the mystery. Hugh Everett III proposed something much more radical. In 1957, Everett introduced what he called the relative state formulation. In this picture, the universal quantum state always evolves according to ordinary quantum dynamics. There is no fundamental collapse. Suppose a particle is in a superposition of two possible outcomes and then interacts with a detector. Instead of one possibility disappearing, the detector becomes entangled with both alternatives. One part of the total state contains one result. Another part contains the other. As decoherence spreads these alternatives into the environment, they become effectively unable to interfere with one another. This idea later became strongly associated with the many worlds interpretation. Before measurement, the superposition is physically present in the universal state. During measurement, the possibilities do not collapse into one winner. They become associated with different decohered branches. An observer in each branch experiences one definite outcome. The mathematics remains continuous. What changes is the structure of correlations within the total quantum state. That is certainly a bold answer. But it is not the only one. Louis de Broglie and later David Bohm developed a very different interpretation, often called pilot wave theory or de Broglie-Bohm theory. Here, particles can possess definite positions even before they are measured. An electron really is somewhere. It follows a trajectory. But that trajectory is guided by the wave function. The wave function still evolves according to quantum mechanics and can pass through multiple regions of an experiment, producing the familiar interference structure. The particle itself follows one definite path, influenced by the guiding quantum state. This restores something that looks much closer to classical realism. But it comes with a price. The theory is explicitly non-local. For entangled systems, the motion of one particle can depend on the configuration of distant particles through the guiding wave function. So de Broglie-Bohm theory gives a clear answer to what exists before measurement, but it does so by abandoning the simple local picture that Bell's theorem made so difficult to preserve. Another possibility is that collapse is real. Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber proposed an objective collapse model in the 1980s. Instead of treating collapse as something introduced only when a measurement occurs, their model modifies quantum dynamics so that spontaneous collapses can happen physically. For small systems, these collapses would be extremely rare. A single particle could therefore remain in a coherent superposition for a long time. But as more particles become involved, the probability that some part of the system undergoes collapse rises dramatically. Macroscopic superpositions would therefore be unstable. Large objects would naturally acquire definite states without requiring a special division between quantum systems and classical measuring devices. In this family of ideas, the transition from quantum possibility to definite outcome is not merely interpretive, it is a genuine physical process. That makes objective collapse theories especially interesting because, unlike many interpretations, they can in principle differ experimentally from standard quantum mechanics under the right conditions. Other approaches rethink the meaning of physical properties themselves. Carlo Rovelli developed relational quantum mechanics. In this view, physical properties are not necessarily absolute features possessed independently by systems. They can instead be meaningful relative to other physical systems. A particle may have a definite outcome relative to one apparatus after an interaction, while another system that has not interacted with that apparatus can use a different quantum description. The emphasis is placed on relations between systems rather than on one universal catalogue of absolute properties. Quantum Bayesian approaches move in another direction. Christopher Fuchs has been one of the central figures in this family of ideas. Here the quantum state is not treated simply as an objective physical object sitting out in the world. Instead, it represents an agent's expectations about the outcomes of possible experiences or interactions. Probabilities describe the beliefs of an agent constrained by the mathematical rules of quantum theory. Measurement then updates those expectations when something new is experienced. These interpretations sound remarkably different. One says the theory should not be forced into a hidden classical picture. Another says all outcomes remain in branching quantum reality. Another gives particles definite positions guided by a wave function. Another makes collapse an actual physical process. Another treats properties as relational. Another places the quantum state closer to information and expectation. And yet many of them reproduce the same predictions for ordinary experiments. That is why the interpretive problem has survived for so long. The laboratory result alone often does not tell us which underlying story is correct. Everyone can calculate the same detector probabilities while disagreeing profoundly about what existed before the detector clicked. This distinction is essential. The experimentally tested structure of quantum mechanics is extremely secure. The meaning of that structure is not settled in the same way. No interpretation has achieved universal acceptance. There is no final scientific vote declaring exactly what the wave function is. So when someone asks what a particle is really doing before measurement, there is not one universally agreed answer waiting quietly in the back of a textbook. There are several serious possibilities. What they share is the same strange evidence. What they disagree about is the reality beneath it. Even the word particle can quietly encourage the wrong picture. It invites us to imagine something tiny and solid, like an invisible grain of sand moving through empty space along a definite route. That image can be useful in some situations. But modern physics describes elementary particles in a deeper way. Quantum field theory treats what we call particles as quantist excitations of underlying fields. An electron is associated with the electron field, a photon is associated with the electromagnetic field. Other elementary particles are likewise connected to their corresponding quantum fields. These fields are not simply mathematical decorations placed around otherwise ordinary particles. They are central ingredients in the modern description of matter and interactions. This viewpoint developed through the work of many physicists during the early 20th century. Paul Adrien Maurice Dirac played a major role in combining quantum mechanics with special relativity and in developing the quantum theory of the electromagnetic field. Pascual Jordan helped establish the mathematical foundations of quantist fields. Vladimir Fock contributed important methods for describing states containing different numbers of particles. Together with the work of many others, these developments led toward quantum field theory, the framework that underlies modern particle physics. One of the major changes introduced by quantum field theory is that particles no longer need to be treated as permanent individual objects. They can be created. They can be destroyed. Their number can change. A photon can be emitted by an excited atom and later absorbed somewhere else. An electron and a positron can annihilate and produce photons. Sufficiently energetic interactions can create entirely new particles, provided the conservation laws and available energy allow it. That would be very difficult to understand if particles were eternal little beads that simply moved around forever. It makes much more sense within a field description. The fields remain part of the theory. What we identify as particles are particular quantist excitations of those fields. This does not mean a particle detection becomes vague. Quite the opposite. When an electron reaches a detector, the interaction can be sharply localized. The detector may register one event in one place. A photon striking a sensor may release an electron within a very small region and begin a chain of amplification. So there is an interesting combination. The quantum state associated with the excitation may be spatially extended. The final detection event can still be local. That is another reason the classical picture becomes misleading. A spread-out quantum state does not require a detector to record a fraction of a particle everywhere. The detector records a discrete interaction. The preparation before that detection can nevertheless involve a state whose amplitudes extend across a large region. Quantum field theory also makes the idea of particle number more subtle than it first appears. In many simple situations, counting particles is straightforward. A detector records one photon, then another. Perhaps an experiment prepares a state containing a known number of atoms. But in interacting quantum field theories, particle number does not always remain fixed. Interactions can create and annihilate excitations, and in some more advanced settings, even the definition of what counts as a particle can depend on the observer and the physical environment. An accelerated observer can describe a quantum field differently from an inertial observer. In curved spacetime, the notion of a particle can become especially delicate. This does not mean that laboratory particle detectors are somehow meaningless. They remain extremely reliable physical devices. It means that the particle concept is not always the deepest or most universal ingredient in the theory. The field description is more fundamental, and that matters enormously when asking what happens before measurement. If we insist on imagining an unmeasured electron as a tiny classical speck travelling through space with one perfectly definite hidden path, we may already be demanding more than the modern theory naturally provides. Quantum field theory does not begin with a little bead and then add some mysterious fuzziness around it. It begins with quantum fields and quantum states. Those states evolve. They can be spread across space. They can interfere. They can become entangled. They can describe situations in which the number of excitations changes. Then, when an interaction with a detector occurs, a localized event can be recorded. So the definite click of a detector should not be confused with proof that an equally definite classical particle trajectory existed at every earlier moment. The detection tells us that an interaction occurred there. It does not automatically reconstruct one unique classical history leading to that event. This brings the entire question into sharper focus. What can we safely say about a particle before it is measured? We can say that a physical quantum system has been prepared. We can assign it a quantum state according to the theory. That state evolves according to quantum dynamics. Its probability amplitudes determine the statistical structure of possible measurement results. If coherence is maintained, different alternatives can interfere. If the system becomes entangled with an apparatus or environment, information can spread and decoherence can suppress observable interference. Those statements are grounded in an enormous body of experimental evidence. The more difficult question is what the quantum state ultimately represents. Different interpretations still disagree. Some treat the quantum state as physically real. Some introduce definite particle configurations beneath it. Some allow all outcomes to remain within a universal evolving state. Some make collapse into a real physical process. Some treat properties relationally. Others place greater emphasis on information and expectation. Quantum field theory does not erase those interpretive disagreements. But it does give us one very important warning. The thing we casually call a particle may already be a simplified way of speaking about a much deeper quantum structure. The detector click is real. The recorded event is real. The predictions are astonishingly precise. But the picture of a tiny object following one ordinary path through empty space before that click is not something modern quantum theory generally gives us for free. Before measurement, the most careful answer is not that the particle is nowhere, nor that it is literally everywhere in the everyday sense. It is that the system is described by an evolving quantum state within a quantum field framework. And the question of what that state is, physically, remains one of the deepest unfinished questions in physics. So what actually happens to a particle before you measure it? The most careful answer is both clearer and stranger than the familiar idea of a tiny object quietly waiting to be found. Once a quantum system has been prepared, its state does not simply freeze until a detector arrives. It evolves. If the system is sufficiently isolated, that evolution follows the dynamical laws of quantum mechanics. The quantum state changes continuously with time. Probability amplitudes shift. Relative phases develop. Wave packets can spread. Different alternatives can remain coherent and later interfere. In that sense, something very definite is happening before measurement. The uncertainty lies not in whether the state evolves, but in what that state ultimately represents. Quantum mechanics gives us an extraordinarily successful mathematical description. What it does not give us, at least not without choosing an interpretation, is one universally agreed picture of the underlying reality. A quantum state can contain a coherent superposition of alternatives. That does not mean we should imagine several ordinary classical particles stacked on top of one another. It means the state contains probability amplitudes associated with different possible outcomes, and the relative phases between those amplitudes can influence what is observed later. Interference experiments make that structure visible. If two alternatives remain coherent, their amplitudes can reinforce or cancel. If information about the alternatives leaks into a detector or the environment, that interference can disappear. The behavior is not what we would expect if the particle simply carried a complete classical description of itself while we remained ignorant of it. The uncertainty principle pushes against that picture as well. Quantum mechanics does not generally allow every incompatible observable to possess an arbitrarily sharp value within the same state. A particle can be prepared with a narrowly defined position distribution, but then its momentum distribution must be broader. A state with sharply defined momentum becomes more spread out in position. That structure belongs to the state itself. It is not merely the result of poor instruments. Bell's theorem goes even further. Experiments show that the correlations between entangled systems cannot be reproduced by the straightforward idea that separated particles simply carry local predetermined answers for every measurement they might encounter. Contextuality adds another restriction. A complete catalogue of measurement-independent values assigned to all observables cannot, in general, reproduce the structure of quantum predictions. So the simplest classical rescue does not work. We cannot merely say that every property was always definitely there in the ordinary sense, and that measurement simply uncovered it. But the opposite extreme is misleading too. It is not correct to say that nothing exists before measurement. Quantum mechanics does not describe an empty void waiting for human attention. There is a prepared physical system. There is a quantum state. That state evolves according to precise rules. It can interact with fields. It can become entangled with other systems. It can retain coherence. It can lose locally observable coherence through interaction with the environment. And all of that can happen with no person anywhere nearby. Measurement itself is simply another physical interaction, although a particularly important one. The system becomes correlated with a measuring device. A microscopic difference is amplified. An electron triggers an electrical signal. A photon creates a detectable event. A particle leaves a mark. Information about the quantum alternatives spreads into larger and larger physical systems until a stable record exists. Environmental decoherence explains much of why those records behave classically. Once a superposition becomes entangled with enormous numbers of environmental degrees of freedom, the relative phases between macroscopically different alternatives become effectively inaccessible. The alternatives stop producing observable interference with one another. From the perspective of the smaller subsystem, the state begins to resemble an ordinary classical mixture. That helps explain why the world around us looks so definite. Chairs do not visibly interfere with themselves. Coffee cups do not appear in coherent superpositions across the kitchen. Large objects are constantly interacting with light, air molecules, thermal radiation, and their surroundings. Their coherence disappears extraordinarily quickly. But decoherence does not automatically answer the final question. Why do we experience one definite outcome? Why does the detector appear to produce this result rather than a visible coexistence of all possible results? That is where interpretation enters. Copenhagen approaches tend to resist the demand for a complete classical account of unmeasured properties. Everettian quantum mechanics allows the total quantum state to continue evolving without fundamental collapse, with different outcomes becoming associated with different decohered branches. De Broglie-Bohm theory gives particles definite configurations guided by a wave function. Objective collapse models propose that collapse is a genuine physical process. Relational quantum mechanics treats physical properties as meaningful relative to other systems. Other interpretations place greater emphasis on information, probability, or the expectations associated with future observations. These are not simply different ways of wording exactly the same philosophical preference. They can make very different claims about what exists before measurement. And yet many of them reproduce the same familiar experimental predictions. That is why no single interpretation has achieved universal agreement. The experimentally established part of the story is much firmer than the ontological one, so the safest answer sits somewhere between two tempting extremes. A particle is not simply a tiny classical object carrying every possible property in secret, and it does not spring into existence only when somebody looks. Before measurement, the system is described by an evolving quantum state. That state can contain coherent alternatives. It carries probability amplitudes and relative phases. It determines the statistics of possible future measurements. It interacts physically with its surroundings, and its behavior has been tested with remarkable precision. What remains unsettled is what that quantum state is in the deepest sense. A real physical wave, a guide to hidden configurations, a branching universal state, a relational description, a tool for assigning probabilities, or something else entirely. That is the peculiar power of quantum mechanics. We can predict what detectors will record with extraordinary accuracy. We can build lasers, transistors, atomic clocks, quantum computers, and entire technologies from the theory. And yet, in the quiet interval before the detector clicks, physicists can still disagree about what reality itself is actually doing. The mathematics is remarkably clear. The picture underneath it is not.